Hello students. In this section of bioenergetics, we will be studying ATP, the role of ATP in cellular metabolism. The story of ATP begins with its discovery in 1929 simultaneously by Kurt Lohmann, who was working with the great biochemist Otto Meyerhof in Germany, and by Cyrus Fiske and Yeladaprada Subarao of the United States. The proposal that ATP is a main intermediary in the transfer of energy in cells is credited to Fritz Lippmann around 1941. Many Nobel Prizes have been awarded for the study of ATP and its role in cellular metabolism, and its importance in understanding molecular cell biology cannot be understated. Biologic systems are essentially isothermic and use chemical energy to power living processes. How an animal obtains suitable fuel from its food to provide this energy is basic to the understanding of normal nutrition and metabolism. Coupling of endogonic processes to exergonic processes. The vital processes, that is, the synthetic reactions, muscular contraction, nerve impulse conduction, and active transport, obtain energy by chemical linkage or coupling to oxidative reactions. In its simplest form, this type of coupling may be represented as shown here. The terms exergonic and endergonic, rather than the normal chemical terms exothermic and endothermic, are used to indicate that a process is accompanied by either loss or gain, respectively, of free energy in any form, not necessarily as heat. In practice, an endergonic process cannot exist independently, but must be a component of a coupled exergonic-endergonic system where the overall net change is exergonic. The exergonic reactions are termed catabolism, generally the breakdown of oxidation of fuel molecules, whereas the synthetic reactions that build up substances are termed anabolism. The combined catabolic and anabolic processes constitute metabolism. If the reaction shown in this figure is to go from left to right, then the overall process must be accompanied by loss of free energy as heat. One possible mechanism of coupling could be explained better if a common obligatory intermediate, I, took part in both reactions, that is, A plus B plus I equals to C plus D. Some exergonic and endergonic reactions in biologic systems are coupled in this way. This type of system has a built-in mechanism for biologic control of the rate of oxidative processes, since the common obligatory intermediate allows the rate of utilization of the product of the synthetic path D to determine by mass action the rate at which A is oxidized. Indeed, these relationships supply a basis for the concept of respiratory control, the process that prevents an organism from burning out of control. An extension of the coupling concept is provided by the dehydrogenation reactions, which are coupled to hydrogenations by an intermediate carrier. An alternative method of coupling an exergonic to an endergonic process is to synthesize a compound of high energy potential in the exergonic reaction and to incorporate this new compound into the endergonic reaction, thus affecting a transference of free energy from the exergonic to the endergonic pathway. The biologic advantage of this mechanism is that the compound of high potential energy E, unlike I in the previous system, need not be structurally related to A, B, C, or D, allowing E to serve as a transducer of energy from a wide range of exergonic reactions to an equally wide range of endergonic reactions or processes such as biosynthesis, muscular contraction, nervous excitation, and active transport. In the living cell, The principal high-energy intermediate or carrier compound is the adenosine triphosphate, ATP. Let's see how high-energy phosphates play a central role in energy capture and transfer. In order to maintain living processes, all organisms must obtain supplies of free energy from their environment. Autotrophic organisms utilize simple exergonic processes like the energy of sunlight in the case of green plants, or the reaction of ferrous ion to ferric ion conversion like in some bacteria. So on the other hand, heterotrophic organisms obtain free energy by coupling their metabolism to the breakdown of complex organic molecules in their environment. In all these organisms, ATP plays a central role in the transference of free energy from the exergonic to the endogonic processes. ATP is a nucleoside triphosphate containing adenine, ribose, and 3 phosphate groups. In its reaction in the cell, it functions as the magnesium ion complex. The importance of phosphates in intermediary metabolism became evident with the discovery of the role of ATP, adenosine diphosphate ADP, and inorganic phosphate denoted by Pi in glycolysis. The free energy change for ATP hydrolysis is large and negative. The hydrolytic cleavage of the terminal phosphoric acid anhydride or phosphoanhydride bond in ATP separates one of the 3 negatively charged phosphates and thus relieves some of the electrostatic repulsion in ATP. The inorganic phosphate in the form of hydrogen phosphate ion release is stabilized by the formation of several resonance forms not possible in ATP. And the ADP ion, the direct product of hydrolysis, immediately ionizes, releasing hydrogen ions into a medium of very low hydrogen ion concentration, about 10 to the power minus 7 moles. Because the concentrations of the direct products of ATP hydrolysis are in the cell far below the concentrations at equilibrium, mass action favors the hydrolysis reaction in the cell. Although the hydrolysis of ATP is highly exergonic, having a free energy change of minus 30.5 kilojoules per mole, the molecule is kinetically stable at pH 7 because the activation energy for ATP hydrolysis is relatively high. Rapid cleavage of the phosphoanhydride bonds occurs only when catalyzed by an enzyme. The free energy change for ATP hydrolysis is minus 30.5 kilojoules per mole under standard conditions, but the actual free energy of hydrolysis of ATP in living cells is very different. The cellular concentrations of ATP, ADP, and inorganic phosphates are not identical and are much lower than the 1.0 moles of standard conditions. And also, the magnesium ion in the cytosol binds to ATP and ADP. And for more